Last time we introduced three different search direction methods: steepest descent, conjugate gradient, and Newton's method. And we saw the Newton's method offered a nice advantage because it used curvature, these second derivatives. But there were a few problems, most that we could work around. But the main problem is that we have to provide second derivatives, and that can be prohibitive for many of these complex engineering analyses, these multidisciplinary analyses. Often providing first derivatives can be hard enough. Getting second derivatives can be really difficult or expensive. So we wanted to look at an alternative that was going to use some of this curvature information, but in a way we didn't have to provide the Hessian. The basic idea is this: you'll be familiar with the idea that we can estimate a derivative from a function just by taking different steps, right? Like taking two nearby steps, doing a secant rule. Well, here's a visual of this, right? So if I evaluate my function at two nearby locations, right, and take this slope, I can get an estimate for a derivative. So in other words, I am getting first order information from function values. Similarly, we could get second derivative information from using first derivatives. So I'm going to show you that first in 1D and then how that would work in ND. So here's just the 1D idea, right? You're familiar with this, f prime. It's going to be equal to the difference in the the function values divided by the x values. Okay, by the way, I didn't mention this at the beginning. If you already watched this, I'm re-recording and deleting the old one because I guess there were some technical glitches with it. But so just in case you're feeling like there's some deja vu. All right, so here we go. We know that one. So now the idea is we could do the same thing. If I turn these into first derivatives, this would become a second derivative. So I could estimate second derivatives from first derivatives. And I'm actually going to move this over to here just in the same step. I'm just doing that because it's going to parallel what we're going to do in ND better. So I could say the second derivative, and I guess I should really write this is for my next iteration, times the difference in the x values this is a, maybe I should be more correct here. This is an approximation, of course. And this is a difference in derivatives, right? I take my derivative in between my last two steps. Okay, we can do the same thing in n dimensions. This is not really a derivation here and just an analogy, but it's going to look similar. So this first term here, my second derivatives would be my Hessian. Although I'm actually not going to write h, I'm going to use another symbol. And the reason why we do that is because this is going to be an approximation for the Hessian. So we generally use a different symbol, in this case, b. Okay, so this is my approximation for the Hessian. If you wanted to, you could think of it as h, but we're going to use b so we can use an equality sign. It's just an estimate. I still have my differences in my x values, which we could also have written this just as my step size, right? S. Oops, sorry. And then this is going to be equal to the change in my first derivatives. All right, and those are my gradients. So gradient of f, x plus 1 minus gradient of f at the previous iteration. So again, the idea is that I'm keeping track of course, my last step. I just have to keep track of my last step, and I have to keep track of my last gradient. But that's going to provide me a way to estimate my Hessian. Okay, so how many unknowns do we have here? In other words, here's my Hessian. Take a minute and recall, what does the Hessian look like, and how many unknowns does it have? And let's just say in terms of n, where n is the number of design variables. Just take a second and try to recall. Remember that my Hessian is a matrix, right? And it's going to be of size n by n. It's a square matrix because this contains, my second derivatives with respect to xi, xj. So it's a square matrix, but it's symmetric. So I don't need to estimate all n squared, just, let's say the upper triangular here. So that's going to be n times n plus 1 over 2 unknowns that I need to estimate. Okay. Now, how many equations do I have? Again, take a second to think about that. So here's this equation I'm using to estimate my Hessian from these derivatives. And so this is a matrix, this is a vector, this is a vector. So this is just a, ax equals b type of equation. But that gives me n equations, right? Each row here of this matrix, that's an equation. So I have n equations. That's a problem, right? Because I have way more unknowns than I have equations. I can help a little bit here because I know a little bit more about the Hessian. I know I've already used the information that's symmetric, but I also know that it needs to be positive definite. Remember, that's kind of that upward bowl shaping type of thing. That's how we can guarantee that our Newton step or our quasi-Newton step is going to give us a descent direction. We need this to be positive definite. So we can require that. That gives us n more equations. So now we have 2 times n equations, but we have, essentially n squared unknowns, n times n plus 1 over 2. So we still have more unknowns than equations. Or in other words, there are an infinite number of possibilities for B. So we're going to have to do something more to come up with an answer here. The first sort of big development here was by 3 folks, Davidoff, Fletcher, and Powell. This is the DFP method from their initials. Their idea was that let's choose, so they were formulating this idea here, and then they went the next step further and said, well, there are an infinite number of approximate Hessians. Let's choose the one that is closest to our Hessian in the previous iteration. And by closest, we're going to use a norm. So if we took the difference between those 2 Hessians and took a norm, we're going to try to minimize that. You may be seeing that this is an optimization problem. We have an objective, which is minimize the distance between my Hessian and the last one, subject to the constraints on this was what this is called the secant rule, right? There's a secant line. So the secant rule, positive definiteness, we could put those constraints in. This is an optimization problem, has a solution, an analytic solution. And this was a really great idea in the field of optimization. A bit after that, there were some further developments by Broyden, Fletcher, Goldfarb, and Shannon. So this is their initials BFGS. And you may have seen that when you've been selecting algorithms. This has become a very popular method for unconstrained optimization. This is the most commonly used method, is this BFGS method. And they had one additional insight, which is this. Remember that for Newton's method, this was our step. P is, we took minus h inverse times f. We solved this linear system, right, with h. And now with the quasi-Newton method, we're doing the same thing, except for we're just using an approximate Hessian, right? So we're using this B instead of the true Hessian. Well, their insight was this, that we're creating an estimate for this Hessian, and then we're solving this linear system of equations. Why not just estimate the inverse of the Hessian directly, right? Then we can, then we don't have to solve a linear system. So, sorry, we're gonna have to create another symbol here, but we're gonna call that V, okay? V is just the inverse of the Hessian, or it's really our approximation of the inverse of the Hessian. This is a really big advantage because solving a linear system is in general an order n cubed operation, whereas just a matrix vector multiply is order n squared. So this is much faster. So again, to recap, rather than try to estimate the Hessian and then do this inverse or really solve a linear system, let's just estimate that inverse directly, and then we can just do a matrix vector multiply, not have to solve a linear system at all. So this is a really great idea. The rest of the mechanics is pretty similar. We're still going to do that optimization problem. We're trying to find the closest solution with the constraints of the secant rule and so on. But now with this additional idea that we're solving for not the Hessian or estimate of the Hessian, but rather the inverse of that Hessian. So here's what it looks like as an optimization problem. We're trying to minimize V at our new iteration minus V of our last iteration, and we're going to take that norm. Okay, so we're just trying to find the closest Hessian, inverse Hessian. relative to our last one. And all the unknowns are the n times n plus 1 entries in this matrix. Okay, so if I was to write that out, I could say, well, we've been saying by varying the entries in V, right? So those n times n plus 1 over 2 entries. We vary those. And of course, if this was all I had, I could get it exactly. I just return the same solution, but that's not very helpful. So I want to impose my constraints, right? I want to impose the secant condition. So the way I'm going to do that, we're doing the inverse Hessian, right? So if I multiplied this by B inverse on both sides, this would become a V on this side. So I'm going to have V times this thing equals this. So that's what I'm going to write. So I've got subject to, these are my constraints. This is just that secant rule, V k plus 1 times the difference in these gradients is equal to my change in x. That's step size, okay? And then my other constraint is that I need V to be symmetric. Hessian symmetric, the inverse Hessian is also symmetric. Okay, so that's the optimization problem. Again, in words, this is sort of our initial motivation that we're using these first derivatives to estimate second derivatives. So this is that secant rule. We also want it to be symmetric. And so we're gonna change those entries. And because there's an infinite number of solutions, the way we're gonna pick a unique one is to say, well, you know, let's use this heuristic that we'll use one that didn't change too much from our previous one. I mean, we kind of think that our function value is gonna be somewhat related to nearby places. So this is kind of something that makes sense, that of all those solutions, a reasonable one is probably one that's not too far off from the last one while meeting this criteria. Okay, and this is called the BFGS method. You might notice that there was additional constraint that we said we need, and that's that the Hessian is positive definite. That also means that the inverse Hessian should be positive definite. We don't actually have to explicitly require this. It turns out that if the last matrix inverse Hessian was positive definite, this one will automatically be positive definite. So as long as our previous one is positive definite, it will always stay that way. So in other words, as long as we start with a positive definite estimate, it'll stay that way the whole time. So we'll be okay. All right, so here's an optimization problem. It's an optimization problem within an optimization problem, if you will, but fortunately this one has an analytic solution. And this is what it looks like. It's a bit lengthy looking, but it's not too bad once we parse it out here. So just to remind you, S, that's our step size. So that's the difference in our X values. This is so we do this at the end of the iteration. We'd compare where we are now compared to where we were the previous iteration. And Y, that's just a shorthand. This is that difference in gradients that's been appearing in those equations. Don't want to write it a bunch of times, so we'll just use the shorthand here, call that Y. So we compute those quantities, and then Y and S appear a bunch of different ways in here. So all we need to do is keep track of our last V, inverse Hessian, our last gradient, and our last X. And so now at our new step, we evaluate those, and we can now get a new estimate for what V should be, that inverse Hessian. Okay, so this method works quite well. Here's that same function we've been looking at with the other cases. Converges rapidly like the Newton method, but we didn't have to explicitly provide those second derivatives. We're estimating it from each iteration. We're getting those gradients, and we're using those gradients to provide better estimates for what that Hessian is. Remember again, the step that we're taking is minus V times the gradient of F. Okay, one thing to note, remember we said that we need to start with a positive definite matrix, a positive definite inverse Hessian here, and then it'll always stay positive definite. The most common one to use is just the identity matrix. Sometimes a scalar times the identity matrix, but that's a positive definite matrix. And notice that if we plug that in, if V is I, then our first step is that. And what's that? You should recognize that. That's steepest descent. So our first step is steepest descent, and that's a reasonable thing to do, right? We know nothing about the Hessian because we didn't provide that. We just know a gradient. So taking a steepest descent step is a reasonable thing to do. And then from there, now we have got a derivative and a new derivative. We can provide an estimate of the Hessian. we can start using some curvature as information to help us accelerate towards the minimum. Okay, so here is an example of what this looks like on the Rosenbrock function. You'll remember that's the function that we've been looking at. That's 2 dimensions, but has that kind of curved valley. And here's an example of the number of iterations. The exact numbers, of course, will vary quite a bit depending on where you start and how you implement these exactly, the type of line search you use and so on. But these are fairly typical characteristics. Steepest descent in particular struggles with this kind of problem because it's got the steep, it's got these kind of steep sides, so it wants to go back and forth, but that valley is curving, and so it can never make too much progress. It makes a lot of really little small steps. Conjugate gradient does quite a bit better because it doesn't try to take such steep directions. It can navigate that curve a lot better. But the Newton's method and Quasi-Newton's method are really efficient because we're using some of that curvature information. I should note also that just comparing iterations is not necessarily indicative of which is more computationally efficient. Remember, an iteration here, we had this algorithm, right, where we have this big while loop where we pick a search direction, we do a line search, we take a step, and then we'd repeat. That whole thing is one iteration. That's what we call an iteration, a major iteration. Within there, we could have many function calls, right? Because during the line search, we may have to evaluate the function multiple times. If we haven't provided a gradient to estimate it, we may have to evaluate it a couple times or multiple times, right? Depending on n, many times potentially. So the cost is not necessarily indicative of just the iterations. This is particularly true when we're comparing Newton and Quasi-Newton, because remember, Newton's method, we're providing the Hessian, which is great, but we have to solve a linear system, and that's an expensive operation. Compared to Quasi-Newton, even though we have a less accurate Hessian or inverse Hessian, we're only doing matrix vector multiplication, which is much more efficient. So each one of these iterations is actually less computationally expensive. So it's hard to compare just on the basis of major iterations per se, but these both work really well. But Quasi-Newton has become very popular. It's going to be the default method on almost any unconstrained gradient-based optimizer. The BFGS method in particular, although I should note that there are other Quasi-Newton methods besides just BFGS. That's one potential method. We chose a particular norm. There are other ways to formulate that, and these other methods, like the SR1 method, can be also quite useful. But BFGS is the most commonly used. Okay, let's see. Well, I should do a little recap. I don't have a ton of space on the slide, so maybe I'll do it on the next one. Ignore the title for a second. I'm just going to briefly review the methods we've talked about here. So remember, steepest descent, our step direction. See if you can remember what that is. It's just minus the gradient of f. Okay, conjugate gradient. See if you remember what that is. It's still, this one's a little harder to remember. It's still we use the gradient, but we also sort of dampen it by using our previous step. Right, we multiply this scalar beta, which we compute, times our previous step. Okay, Newton's method. What's that? See if you can remember what that is. This is minus the Hessian inverse times the gradient. This we got, remember, we did a Taylor series expansion, got a second order function, took a derivative, set it equal to 0. This is what we got. Okay, Quasi-Newton, that's the one we just saw. What does that look like? What's the difference? Difference is that one that we're estimating, but we're estimating the inverse Hessian, so it's just a matrix vector multiply. Okay, so limited memory Quasi-Newton methods. It's a bit more of an advanced topic, so I'm not going to fully cover it here. I put some more details in the book that you can look at if you're interested. I just want to give you kind of a feel so you can be aware these things exist. You might, for example, see this in some of the algorithms as a choice, L-BFGS. That's a limited memory BFGS. The idea is that we have to store this, well, actually inverse Hessian, which is a matrix, and that can be prohibitive if the number of design variables becomes really large. Sometimes we solve problems with, say, millions of design variables or more, and now the inverse Hessian is a n by n matrix. So that's, a million times a million entries that we have to restore, and that can require a prohibitive amount of memory. Fortunately, we can use kind of this recursive form, the recurrence relationship, to calculate this. We don't actually ever have to form V, because all we actually care about is this product, V times the gradient of F. And from storing some vectors, we can actually calculate that by using this recurrence relationship, basically a history of vectors. So if we saved all these gradients from our first iteration forward, we could just use this sort of iterative process and calculate this without ever storing the Hessian. Now that alone doesn't actually help, because now we're storing this huge history of vectors. So the approximation that we're going to make, and this is again sort of an approximation, but a very good one, is that we don't need a full history, in part because my Hessian, like 20 iterations ago, probably doesn't have much relationship to my Hessian now. I'm pretty far away. So I just save, let's say, in my last 10 iterations or so, just vectors, and then I can estimate this this update using way fewer resources, because vectors, let's say I store 10 times n could potentially be way smaller than n squared when n is a big number. So if I had 10 gradient vectors that are of size n, that's much less memory than storing this n squared matrix. And again, this is a bit more of an advanced topic, because especially as we're beginning, we usually don't have such huge problems, but just something to be aware of. And if you're interested, take a look more in the text, and you can get into more depth by looking also in the literature. Okay, so that kind of recaps what we'll call line search methods. Next time, we're going to talk about a different approach called the trust region method. We've been doing the steepest descents, conjugate gradient. All of these are what we call line search methods, because we're picking a direction and doing a line search. We're still going to be looking at unconstrained gradient-based optimization, but we'll look at an alternative approach, and we'll do that next time. We'll see you then.